Hello friends, my name is Sonu and I am the student of BSc Chemistry Honors second year. Today we will prepare a video for the visually impaired students on the topic of coordination compounds. Coordination compounds represent a special class of compound. In the early days of chemistry, it was very difficult to explain why stable molecules which are capable of existing independently should react in stoichiometric amount to form several new and stable compounds. For example, an aqueous solution of cobalt chloride react with varying number of another stable molecules such as ammonia in the presence of oxygen to give a series of well-defined crystalline compound of composition COCl3.6NH3 or COCl3.5NH3 or COCl3.4NH3 and COCl3.3NH3, which were approx named according to their color. Such compounds were named complex because they appeared unusual and were difficult to understand. Today thousands and thousands of such type of compound are known. The credit of explaining the bonding in those complex goes to Alfred Warner, who was awarded Nobel Prize in Chemistry in 1913 as a fitting recognition of his accomplishment. According to Warner, complexes of coordinates complex represent a special class of compound in which the central metal atom or ion is surrounded by a number of ions or molecules. These compounds are now popular called coordination compound. Coordination compound have also been found to be of biological importance. Iron compounds are found throughout the plant and animal kingdom. Iron is present in hemoglobin, the molecule in red blood cells that is responsible for the transport of oxygen from lungs to the other tissue of the body. Myoglobin found in muscle tissue is a similar molecule containing iron. Myoglobin takes oxygen from hemoglobin, holding it until it required by the muscle cells. Chlorophyll is the another magnesium compound in which magnesium is surrounded by four nitrogen which are part of the coplanar fused ring system. Chlorophyll plays an important key role in the biological process known as photosynthesis, in which carbon dioxide and water are converted into sugar molecule. Apart from the biological usefulness, coordination compounds find extensive application in processes such as water treatment, soil and plant treatment. Some of the coordination compounds have recently been used in versatile catalysts for the production of organic or industrial scale. Increasing use of coordination compound is being witnessed in many metallurgical processes, especially in electroplating. In this chapter, we will review some of the terms commonly used in the coordination compound, special reference to the Werner coordination theory. Werner theory of coordination compound. A number of theories by different scientists were put forward to explain the structure and bonding of coordinate compound. However, none of proposed theories could explain the satisfactorily all the properties of coordinate compound. It was only in 1893 that Alfred Warner could successfully the bonding in the coordination complex, the theory which laid the foundation of coordination compound, popularly known as Werner's coordination theory of coordination. In recognition of this contribution, this frontier area of chemistry, Werner was decorated with the Nobel Prize in Chemistry in 1913. The postulates of Werner theory are following. Every element exists two types of valency known as primary valency and the secondary valency. The primary valency is ionizable where the secondary valency is non-ionizable. The primary valency refers to the oxidation state and of the element or ion where the secondary valency corresponds to the coordination number. Every metal atom has a fixed number of secondary valency is that coordination number. Every metal atom tries to satisfy both its primary and secondary valency. Primary valency are satisfied by negative ions and the secondary valency are satisfied either by the negative ions or by the neutral molecules. In some cases, a negative ion may satisfy both primary as well as secondary valencies. The primary valency are non-directional and the secondary valencies are directional and are towards the fixed position in the space. As a result, the secondary valency determines the geometry of the coordinate complex. For example, if the metal ion has 6 secondary valencies, these are directional towards secondary valencies. These could be directed either towards four corner of tetrahedral or a square planar arrangement around the central metal atom. It is thus the number of arrangement of these secondary valencies that determine the stereochemical of the coordination compound. Let us try to explain the bonding in various cobalt amine compound formed on the basis of Riverdale postulate of Werner theory. In all the four cobalt amine complex 2COCl3.6NH3, COCl3.5NH3, COCl.4NH3 and COCl3.3NH3. The secondary valence is 6 while the primary valence is 3. Each structure is written satisfy both the primary as well as the secondary valency. Isomerism in coordination compounds. Isomerism is one of the most interesting aspects of molecular structure. If you recall, organic chemistry is incomplete without the phenomena of isomerism. Likewise, the chemistry of coordination compound and complex is rich of the isomerism. Many coordination compound and complex have the same chemical formula but different structural arrangement. Such type of compound are called isomer because of different structural arrangement. The isomer have different physical and their chemical properties. Coordination compounds have various type of isomerism. Important type can be broadly classified into two types: structural isomerism and other is stereoisomerism. Structural isomerism in coordination compound can be classified further according to their five different type, namely ionization, hydrated, coordination, linkage, and coordination position. On the other hand, stereoisomerism are broadly classified into two types, namely geometrical and the optical. Structural isomerism. These isomerism have same molecular formula but different structural arrangement of atom or group of atoms around the central metal ion. Let us discuss the various type of structural isomerism one by one. First is ionization isomerism. This type of isomerism arises due to the exchange of an ion within and outside the coordination sphere. As a result, these isomerism give different ion in solution. For example, two compounds CONH3Br SO4 and CONH3 SO4Br represent ionization isomerism because the compounds are formed by exchange of bromine ion in the coordination sphere with the sulfate ion outside the coordination sphere and vice versa. Both the compounds have different physical properties. For example, the bromo complex is red where the sulfato complex is violet. The chemical properties of the two ionizable isomerism are also different. The red isomerism form the off-white precipitate AgBr with Ag positive ion but gives no precipitate with barium ion. On the other hand, the violet isomerism reacts readily with barium ion to give the white precipitate of barium sulfate. The reactions show above indicate that the ions bound the coordination sphere are not free to react. In summary, these ions in solution while bromine gives bromine ions in the solution. And next is hydrated isomerism. This type of isomerism is very closely related to ionization isomerism. In hydrated isomerism, water is exchanged between the complex with the square bracket and the rest of the complex. The, the classical example of the hydrate isomerism is shown by 3-hydrate chromium chloride of composition CrCl3.6H2O. In other words, 3 isomerism of CrCl3.6H2O are known, which are CrH2O 6 times Cl3, CrH2O 5 times dot Cl, Cl2.H2O, and CrH2O 4 times Cl2 bracket dot Cl dot 2H2O. The violet color compound does not lose any water molecule or dehydration when kept on the concentrated sulfuric acid. However, addition of silver nitrate solution precipitate all the 3 chloride ion. The green colored compound loses one water molecule on dehydration with concentration H2SO4, whereas the dark green colored compounds loses two water molecule on dehydration with H2SO4. Addition of silver nitrate precipitate to chloride ion in case of green colored compounds and one chloride in case of dark green colored compounds respectively. Hydrate isomerism is also observed in the following example: Cr ethylene diamine twice H2O dot Cl wall bracket Cl2 and CO ethylene diamine twice times Cl2 wall bracket Cl dot H2O. Hydrate isomerism can be considered as special case in ionization isomerism. And next is coordination isomerism. Coordination isomerism occur in the compound in which both the cationic and the anionic part to the metal ion. The isomerism arises due to the exchange of one or more ligand between the cationic and anionic complex of the coordination compound. As example of coordination isomerism is CrNH3 6 times dot FeCN 6 times and FeNH3 6 times dot CrCN 6 times. Other commonly occurring example of coordination isomerism are. And next is linkage isomerism. Linkage isomerism arises because some ligand can coordinate to the metal ion in more than one way. Such ligands are called ambidendrite ligand. Such linkage isomerism is exhibited by the complex containing ambidendrite ligands. Commonly example of ambidendrite ligands that show the linkage of isomerism are NO2 versus ONO negative, CN negative versus NC negative, and SCN negative versus NCS negative, where the coordinating atom is written first in each pair. The other ligands known to form linkage isomerism include SECN negative, SO3 2 negative, S2O3 2 negative, and CS3 whole twice SO, and urea or thiourea, etc. Of all the ligands, thiocyanate have received considerable attention. The coordination complex exhibited by the ligand can attach by the metal either through sulfur called S-bonded thiocyanate or through nitrogen called N-bonded thiocyanate. And next is coordination position isomerism. This type of isomerism occur in the polynuclear Bliss complex is that complex having more than one metal atom. This type of isomerism arises due to the interchange ligand between the different metal centers. Stereoisomerism. Stereoisomerism have the same atom to atom bonding sequence, but the atom differ in the arrangement in space. Coordination compounds exhibit two types of stereoisomerism. First is geometrical isomerism and other is optical isomerism. In geometrical isomerism, cis and trans in alkenes, and the optical isomerism non-superimposable mirror image that have a unique property of rotating the plane polarized light. These are detailed below. First is geometrical isomerism. Geometrical isomerism arises when the atom bonded directly to the metal have different space arrangement. The simplest example of geometrical isomerism in coordination compound is the cis-trans isomerism. Two ligands occupying the position adjacent to one another around the metal atom are called cis-trans isomerism. Alfred Werner to prove that unlike carbon transition metal often have square planar geometry, planar complex are four coordinate complex. In natural question arises, do tetrahedral complex are also four coordination show cis-trans isomerism? The answer is no. This is because all tetrahedral complex such as Ma4, Ma2B2 or MABCD, where ABCD represent the ligands, can exist in one geometrical form in which all positions are adjacent to each other. Werner was successful in showing the platinum second complex exists two geometrical forms, cis and trans. A commonly observed example in this type of complex shown by the coordination compound is that platinum pyridine second and NH3.Cl, which exist in cis and trans form. Geometrical isomerism in complex with coordination number 4. The complex with the coordination number 4 can either acquire square planar or tetrahedral geometry. A regular tetrahedral species of type Ma4, Ma2B2 and MABCD, where ABCD are the ligands, exist in only one geometrical isomerism. This is because all the positions are adjacent to one another in the tetrahedral geometry. As a result, tetrahedral complex do not exhibit the geometrical isomerism. On the other hand, a planar species of the formula Ma2B2 can exist cis and trans form, and therefore they will form geometrical isomerism. The chemical and physiological properties of the geometric isomerism differ greatly. For example, platinum dichloride diamine is a plain orange-yellow compound with a solubility of 0.25 gram per 100 ml in water. This compound is used for the chemotherapy treatment in cancer patients. On the other hand, trans PTCl2.NH3 twice is deep yellow compound and has a very limited solubility of 0.037 gram per 100 gram of water in water. Some other compounds of this type are found by the complex of platinum second, nickel second, and copper second, arsenic second, etc. It is important to note that the geometrical isomerism have been isolated only in one case, which is platinum second complex. Is primarily because the platinum second complex are far more stable than the complex formed of the other metals. The square plane complex of the type of Ma2Bc shows geometrical isomerism in case where the similar A group are either adjacent or opposite in each other case. It is important to appreciate that geometrical isomerism cannot be found in complex conforming the formula Ma4, Ma3b or MAB3. The student is advised to draw the possible spatial arrangement of these cases, convinced that all arrangements are exactly equivalent. Geometrical isomers in octahedral complex. Of all the metal complex reported till to date, the largest percentage containing the 6 coordination metal atom of iron. All the 6 coordinated complex are either octahedral or distorted octahedral. In case of octahedral complex, there are more possible geometrical isomerism than in case of square planar complex. An octahedral complex of the type Ma6 or octahedral complex confirming The arrangement of atom as Ma6 or Ma5b will not show cis trans or geometrical isomerism. On the other hand, on octahedral complex of formula Ma4b2 can display cis and trans isomer as shown below. Compound of the formula Ma3b3 known to show two geometrical isomerism when the three ligands with the same donor atom are on the same triangle faces of the octahedron. The isomerism is given the name facial or face isomerism. In other words, the facial isomerism with identical three ligands form a triangular face of octahedron. The angle AMA and BMB in the facial isomerism are over 90 degree. On the other hand, when the three ligands are on the same equidistant plane of the octahedron, the isomer is named is meridional or Mer isomer. In case of meridional isomer, the angle AMA and BMB correspond to 180 degree. In brief, when the three identical ligands are found in the corner of triangular faces of octahedron, the isomer is facial. When the three identical ligands are found in the corner of square plane, the isomer is meridional, shown in the figure. The commonly observed example of face and mer is observed in the compound coordination compound CONH3 thrice Cl3, which exists in two forms. Octahedral complex of the type Ma6 or Ma5b do not show cis trans isomer because Ma6 or Ma5b exist only the cis form and not the trans form. The possibility of the geometrical isomerism increases dramatically as the number of different kind of ligands increases. The octahedral complex with six different ligands of the type of Ma, B, C, D, E, F will show theoretically as many as 15 geometrical isomerism. However, practically on the three isomers have been same isolated in non-compound PT C5H5N NH3 NO2 ClPRI where all the six ligands are different. Now the next isomerism is optical isomerism. Substances which are capable of rotating the plane polarized light are called optically active substance. An optically active substance cannot be superimposed on the mirror image. Molecules that have superimposable mirror image are called chiral, a Greek word for hand. Pair of non-superimposable molecules are called enantiomer, a Greek word for both. We have already learned that the essential condition for a substance to show optically activity is that the substance should not have a plane of symmetry. The most common example of chiral compound is found in case in which four different atoms are attached to the tetrahedral carbon atom. The optical isomerism have same physical properties such as melting point, boiling point, density and solubility in common solvent. These, however, differ in rotating the plane polarized light. The two isomerism rotate the plane polarized light to an equal extent but in opposite direction. The term optical isomerism is used because the effect involves light. At one time, it was thought that optically isomerism exists only in one carbon compound. However, it exists in inorganic compound as well. Let us discuss the optical isomerism in coordination compounds. Optical isomerism in compound with coordination number 4. Square planar complex with CN4 in general do not exist optical isomerism as these contain plane of symmetry. On the other hand, tetrahedral complex optical isomerism because there is a no plane of symmetry in tetrahedral molecule. However, it is extremely different to isolated optically active tetrahedral complex when all the attached group are different. This is primarily due to the labile nature of these complex. Some of the tetrahedral complex of BE2, B3, Cu2 and Z and second containing the unsymmetrical bidendant ligand have been resolved into the optically active isomerism. An interesting example of optical isomerism is shown by the complex Bis-benzoyl alactonate, beryllium second ion are shown in the below. Optical isomerism in compound having the coordination number 6. Optical isomerism is well known in case of octahedral complex. Optical activity is theoretically possible if all the 6 ligands surrounding the metal atom are different. This appears to be an ideal example as there would be no plane of symmetry in the molecule, which is prerequisite for a complex to show the optical activity. However, it is extremely difficult to isolate such a compound where all the 6 ligands surrounding the metal atom are different. However, it is far easier to isolate optically active 6 coordinate compound with chelating ligands. Some of the common examples are found to the octahedral complex of this type: MAAA3, MAA2B2 and MAAB2X2. Complexes of type MAA2X2. Coordination compound are complex of type MAA2X2 will show both the geometrical as well as optical isomerism of the cis and trans form. It is a cis isomerism that further optically active. The trans form is optically inactive as the isomerism has got a plane of symmetry. The three isomers arising out of the MAA2X2 are shown by the complex ion. Now we move to the next topic, chelates. Chelates are the cyclic or ring compounds that are formed when ligands bind with the central atom or ion through two or more donor atoms of a ligand. Such a ligand that binds the metal atom through two or more atoms is called a chelating ligand. In the process is called chelation. Chelating ligands are basically multidendent ligands which upon coordination with the central metal atom result in the formation of cyclic compounds. All the type of bidentate, tridentate, tetradentate and pentadentate and hexadentate ligands are known to form a variety of chelates. For example, ethylene diamine ene form a chelate with copper ion CuH2 NCH2 CH2 NH2 2 positive or CuEn twice 2 positive. Chelates or chelated complexes have been found to be more stable than similar complex unidendate ligands. This is primarily because the dissociation of chelate with its cyclic innovation breaking of two bonds rather than one in non-chelated complex. Another important chelating ligand is dimethyl glycine DMG, which is conventionally used to estimation of nickel in gravimetric analysis. Factor affecting stability of the complexes. It has already been pointed out that chelate complexes are more stable than similar complex with unidendate ligands. Let us determine the factor affect the stability of chelates. First is chelate effect. Chelate complex formed by the multidendate ligands such as ethylene diamine, acetylene glycoside ACAC negative, terpyridine TER or ethylene diamine acetic acid EDTA have been found to be more than those of found to monodendate ligands such as H2O, NH3 or pyridine. This increase the stability of complex containing chelating ligands is called chelate effect. For example, the copper complex chelating ligands ethylene diamine is more stable than the corresponding complex with ammonia. This increases the stability of ethylene diamine complex of copper over the ammonia complex, easily explained on the term of favorable entropy during chelation. In the brief, the stability of chelated complex can be explained due to an increase in the entropy system. Number of chelate rings. A chelate in which more number of rings are formed is more stable. In other words, the number of chelate rings is the complex, the greater is the stability of complex. A comparison by stability constant for the complex shown table below show the ethylene diamine is more stable than the ammonia molecules. Chelates or chelated complexes have been found to be more stable than the similarly complex unidended ligands. This is primarily because the dissociation of the chelate, which is cyclic breaking of two bonds rather than one in non-chelated complex. And third is size of chelate rings. The stability of the chelates depend primarily upon the size of ring formed. Unlike organic ring system, metal chelates with 5 member ring have been found to be more stable. This is because the metal atom are larger than the carbon atom in organic molecule, and the bond angle that the metal atom will be 90 degrees square planar or octahedral complex, in contrast to the optimum angle of 109.5 degree for carbon. A number of 5 member chelate rings are formed with various chelating ligands: ethionine, diamine, oxalate ion, glycine, and dimethylglycine (DMG). Our chelating ligands such as acetylactone form stable 6 member ring having the some aromatic character in result of resonance stabilization. For example, acetylacetone form neutral complex with trivalent metals such as TiACAC second, chromium ACAC thrice, and COACAC thrice. In the complex, the rings are unsymmetrical with MO bonds equal in the length, the CO bonds equal, and the two CC bonds equal in the length as a result of resonance equivalence. Rings of size greater than 6 are known as a very they are not very stable. The instability of higher member rings can be shown. Extra energy required to bring the coordination atom of chelating ligands close to the metal ion for bonding against electrostatic force. Decrease effective concentration of the other end of the ligands for large chelation molecule that form 7 or 8 member rings. Scarcity of finding sterically non-crowded ring configuration. Large bulkier ligands form less stable complex than the smaller ligands. Ethylene diamine complex, for example, are stable than those of corresponding tetramethyl substituted derivative. This is because the bulkier group near the donor sites offer mutual repulsion among the ligands. Next topic is effective atomic number. The first attempt to account for the bonding and coordination complex was made by Sidgwick in 1927. Sidgwick, in fact, extended by the octet theory of G. N. Lewis to coordination compound by suggesting new term called coordinate bond, in which the metal atom or ion accept electron pair from donor atom called ligands. In other words, ligands were considered by to be Lewis space which donated usually one electron pair to metal ion acting as Lewis acid. He further stated that transition metal accept electron pair from donor until the metal atom in the complex acquired next noble gas configuration. This is popularly referred to the effective atomic number. Thus, effective atomic number EAN represents the total number of electrons possessed by the central metal ion in the complex and the central donated by the ligands. Valence bond theory. Valence bond theory was developed by the Linus Pauling, who provided the first detail explained the electronic structure of coordination complex. The explanation is an extension of covalent bond discussed in the simple molecule. According to a view of covalent bond is formed by the overlap of atomic orbital, one from each bonding atom. In the usual covalent bonds formation, each orbital organized hold one electron, and after the overlap, a bond is formed that holds two electrons. In the formation of coordinate covalent bonds in a complex, however, an orbital containing two electrons overlap unoccupied orbital on the metal atom. Valence mode approach is the simplest of the three theories proposed by the explaining bonding coordination compound. The theory is successful explain the structure of magnetic properties of coordination compounds. The silent feature of this approach are: first, the central metal atom or ion in the complex offer a number of unoccupied orbital, which is to be the coordination number of the metal atom for the formation of coordinates bonds with the ligands. It means that if the coordination number of the metal is 4, the metal offer 4 unoccupied orbital in the bond formation. Similarly, the coordination number of metal is 6, the metal offers 6 unoccupied orbital for bond formation. The appropriate atomic orbital sp and d of the metal hydrides to give a new set of orbital equivalent of equivalent energy called hybrid orbital. These hybrid orbital have definite direction properties. A result, all the hybrid orbital are directed towards the ligands in accordance with the geometry of resulting complex. The various type of hybridization and their geometrical are given. If the hybridization is sp and the coordination number is 2, then the arrangement will be linear. If the coordination number is 3 and hybridization is sp2, the arrangement will be trigonal planar. If the coordination number is 4 and the hybridization is sp3, then the arrangement will be tetrahedral. If coordination number is 4 and the hybridization will be dsp2, the arrangement will be square planar. If coordination number is 5 and the hybridization is dsp3, the arrangement will be trigonal bipyramidal. If coordination number is 5 and the hybridization is sp3d, then the shape is trigonal bipyramidal. If the coordination number is 6 and the hybridization is dsp3, the shape is octahedral. Similarly, coordination number is 6 and the hybridization is sp3d2, the shape is octahedral. Complex with coordination number 4. The coordination compound with coordination number 4 are well known. Complex with coordination number is 4 can either tetrahedral or square planar depending upon their whether the hybridization is sp3 or dsp2. Some of the most commonly found examples are discussed below. Formation of nickel cyanide 4 2 negative ion. The oxidant state of nickel is complex is +2. We can represent the electronic configuration of Ni2 positive ion by losing 2 electrons from the outermost shell 4s orbital. The electronic configuration of Ni is argon 18 3d8 4s2. Thus, the electronic configuration of Ni2 positive ion is argon 18 3d8. The 8 electron represent the d orbital will occupy in such a way that we shall have 3 of the 3d orbital occupied by the 2 electron, while the remaining 2 3d orbital are singly occupied as shown in the figure. There are two ways in which the coordination complex of nickel the coordination number 4 can be formed. If the complex involves sp3 hybridization, it will have tetrahedral structure. On the other hand, if the complex involves dsp2 hybridization, it will have square planar structure. In case of complex XY tetrahedral structure, the hybridization is sp3. It means that the unpaired 3d electrons are not affected. As a result, the coordination compound with sp3 hybridization will be paramagnetic as in the case with Ni2 positive ion itself. However, the square planar structure which involve dsp2 hybridization require one of the 3d orbital vacant of hybridization. This is possibly only if two unpaired 3d electrons are paired up. Makes one of the 3d orbital empty. During the exercise, no unpaired electrons are left in the complex should be diamagnetic. It has been experimentally observed that complex NiCN42 negative is diamagnetic with conclusive indicate that hybridization is dsp2, and secondly it has no unpaired electron shown in the figure. Formation of NiCl42 negative. The oxidation state of nickel in NiCl4 2 negative is plus 2. This is obtained by the loss of 2 electrons from the 4s orbital of nickel as shown. Experimentally, the complex has been found to be paramagnetic corresponding to two unpaired electrons. It is implies that 3d orbitals are not distributed and the complex involve sp3 hybridization. As a result, the structure of the complex is tetrahedral as shown in the show figure. Formation of CuNH3 4 2 positive. As the inspection at the complex of CuNH3 4 2 positive reveal the oxidation state of copper in the complex plus to the resulting electronic configuration of Cu2 positive is argon 18 3d9. According to the Hund's rule, the 9 electrons occupy the 5 3d orbital and only one orbital is singly occupied. In order to accommodate first ammonia molecule around Cu2 positive, the metal ion exists two possible geometrical arrangement for the complex. If the complex is tetrahedral, it will involve sp3 hybridization and complex will be paramagnetic. On the other hand, if the complex happen to square planar, it will involve dsp2 hybridization and the complex will be paramagnetic again. Now a natural question arises, which of the two structure of CuNH3 4 2 positive is true tetrahedral or square planar? Crystal structure determined of the compound has revealed that the complex has the square planar structure. It implies that dsp2 hybridization must be involved with one of the 3d orbital made available for the hybridization. This can be done by the promoting the one electron from the 3d to higher energy vacant 4p orbital. Once the electron is promoted into the higher energy orbital, it becomes unstable and can be lost easily. It means that Cu2 positive complex can be easily oxidized to Cu plus 3 complex. However, it is not true because Cu3 positive ions are practically unknown. It is believed that above representation of CuNH3 for 2 positive ion is inadequate. Although it explains the square planar geometry together with the magnetic moment of complex, it fails to explain the Cu2 positive can be easily oxidized to Cu3 positive. The anomalous behavior can be easily answered if the considerable the electron in the 3d orbital are not performed at all the hybridization involved outer 4d orbital. This model explains not only the square planar geometry together with the magnetic moment but also the stability of Cu2 positive ion, which do not undergo easy oxidation to Cu3 positive by loss of electron. Formation of complex with coordination number 6. Formation of CrNH3 6 times 3 positive complex ion. The oxidation state of chromium in CrNH3 6 times plus 3 is plus 3. The electronic configuration of chromium is 24 will be argon 18 3d5 4s1. Thus chromium in plus 3 oxidation state will be formed by the loss of 1 4s and 2 electron are shown in the figure. 2 vacant 3d orbital 1 4s and 3 4p orbital of chromium are hybridized to get 6 dsp2 hybrid orbital. In other words, Cr3 positive provides 6 empty orbital to accommodate 6 pair of electron from 6 molecule of ammonia. The resulting complex CrNH3 6 3 positive involve dsp3 hybridization and it will be octahedral in structure. The presence of 3 unpaired electron in the complex make it paramagnetic. Other is formation of CONH3 6 times plus 3. The electronic configuration of cobalt 27 will be argon 18 3d7 4s2. Oxidation state of cobalt in the complex is plus 3, which obtained by the loss of by 2 4s and 1 3d electron. Thus the electronic configuration of CO plus 3 is argon 18 3d6. In the arrangement, there are 4 unpaired electrons, 1 paired electron by the 3d orbital. In order to acquire octahedral geometry, the complex should have d to sp3 hybridization. It can be achieved in two ways. These two electrons in the 3d orbital are either paired up with electron in the other 3D orbital, thus leaving the other 3D orbital empty. On the two 3D electron can be pushed into higher energy vacant state or 5s orbital, since pairing of electron require less energy or promoting to higher energy orbital. One electron prefer to pair up two vacant 3D orbital or one 4s and three 4p orbital of cobalt are hybridized to give 6d2sp3 hybridized orbital. In other words, CO3 positive provides 6 empty orbital to accommodate 6 pair of electron from 6 molecule of ammonia. Since there are no unpaired electron in 3D orbital complex, so the complex should be diamagnetic. Experimentally, it has been found the complex is also diamagnetic. Next is formation of COF63 negative. As already discussed, the electronic configuration of cobalt is 27 will be argon 18 3d 4s2. The oxidation state of cobalt is COF63 negative is plus 3, which is easily achieved by the losing of 2 electron from 4s and 1 electron from the 3d orbital. The electron configuration of CO3 positive will be argon 18 3d6. The complex sign of COF6 3 negative has been found to be paramagnetic, which suggests that the presence of unpaired electron. However, the behavior is together different that we observed in the case of CONS363 positive to amount to the same. The octahedral geometry in the case of COF63 negative cannot be distributed to D2sp3 as found in the case of CONS362 positive. Now, limitation of valence bond theory. The valence bond theory extended by the Linnaeus proposing to coordinate compound in terms of orbital hybridization was successful in interpreting the geometrical shapes of most of complexes. However, the theory failed to account for the several properties associated with the complex. First, it failed to explain the color and spectra of complexes. It failed to explain the differences between the measured and calculated magnetic moment. Although the theory is successful in predicting the number of unpaired electrons in the complex, it also failed to explain the why the magnetic moment value varies with the temperature. And last is the theory failed to explain or offer any concept explain to relative stability of the complexes. Thanks.